Thank you. So I guess I should just say, maybe it was implicit earlier, please feel free to interrupt at any time with questions. So slow me down if necessary. So I want to begin by something, this is a 1930 paper by Zermelo. Didn't really get a lot of attention at the time, but I think there's some interesting things you can do with it. So let me get rid of his, why is it not letting me draw on my screen? Okay, well, I was gonna draw a picture off to the side of like what was going on, but I'm not seeing that. Oh, here's the options to draw, maybe. Okay, so, all right, I'm not having a good time with the Zoom at the moment. Okay, so I apologize. I was gonna draw a nice picture off to the side of the set-theoretic universe. Let me kind of do it with my hands. So Zermelo, you build up, you start with the empty set, you kind of iterate the power set operation along the ordinals that generates all the sets. And Zermelo had this idea of kind of rather than, looking at a single universe of sets, the idea was you keep building up forever. And he's like, okay, well, this is just some small set and some larger universe that can see it. You keep building up beyond that. You think you've got the universe. Well, no, that's just a set in some large universe. You keep building up before. And so we had this idea that there's these kind of like larger and larger universes. And he wanted this idea of rather than just something like this single theory of sets, this like meta theory of sets, he said. So he calls these boundary numbers. Today we call these inaccessible cardinals, these heights he was looking at. And okay, this didn't get a lot of attention at the time for various reasons. I want to historically and just very wrongly suggest that the reason it didn't get attention is we didn't yet have the logical tools to really understand it. And what logical tools would those be? Is it would be the tools of modal logic. This is an inflationary domain. We're adding more elements. If you think like as you move larger and larger, we're just adding in more elements. There's this natural modal interpretation of that. And this is the natural tool to really understand his proposal. Okay, so how would we interpret Zermelo's view then in modal logic? So what are the worlds? So we're going to kind of work as our background theory as ZFC plus whatever. So we have this single universe of sets, and we're going to interpret Zermelo's multiversal view inside that. So your worlds are V kappa. V is this hierarchy of building up the sets. You build it up to an inaccessible cardinal. All of those stages are the worlds. And so how do we interpret the two modal operators? When is something possible? Well, it's possible at V kappa if there's some larger world where it's true. When is it necessary at V kappa? If it's true at all larger worlds. So it's pretty natural interpretation of these. And then you can ask interesting questions about this. Namely, kind of the big question that gets asked in the series, you want to know, what is the modal logic of this sort of potentialism? Okay, so in more detail, what do I mean by saying the modal logic of this? Is we can look at propositional modal assertions, so things that don't have any set theoretic context, and we want to take these propositional variables and plug in statements with set theoretic context. And we want to know which ones of these are valid. And so if you've done any work with like crypt keyframes, you might say, okay, here's this sort of crypt keyframe. What are the propositions that are valid on that? That sort of idea, but rather than just arbitrary assignments of truth and false, we just want to plug in set theoretic formulae. And kind of, we could also ask then, does this modal logic, do these validities depend upon the world? Is it always the same? Does it differ? Can we nail down where that happens? Okay, so let's try to explore this question. So the easy half of this, if we're going to know exactly what the modal validities are, we want to approach it from below, approach it from above. So lower bounds tend to be easier. So this is an observation. The modal theory S4.3 is a lower bound for the modal validities in any world. Okay, if you know what S4.3 is, this is immediate. Basically, S4.3 is valid for linearly ordered frames, and the V kappas are linearly ordered. It's just going up or down. So I don't want to belabor this, but let's look at maybe this 0.3 axiom, the 0.3 and S4.3. And so what does it say? So two things are possible. P is possible, Q is possible. What does that mean? It means we can go up to some larger world to find P, or we can go up to some other larger world to find Q. So because these are, excuse me, because these are linearly ordered, either the P world comes before the Q world or vice versa. So if the P world comes first, we could move up. P is true. Q is still possible because we could move further up. Or if the Q world came first, Q is true, we could move up to P. So this complicated looking expression is really just expressing some sort of linearity on the underlying accessibility relation. Similarly, like S says that it's reflexive, force says it's transitive, and then these two just kind of come along for free. Okay. So nothing very deep then to get a lower bound. It's just noticing we have a linearly ordered frame. And so that's going to give us at least S4.3. So more difficult then is, can we get an upper bound? So can we show that some things are not valid in this potentialist frame? Okay. And so with some work, you can show that S5, so we're going to take all the basic axioms we had before, and we're going to add in this sort of maximality principle. If something is possibly necessary, it has to already be true. And so this is going to be an upper bound. So this is, if you had any statement, if you can extend so that it's true forevermore, that would mean it's already true. And so anything outside of S5, typically considered a pretty strong modal logic, just isn't going to be valid. Okay. This is the harder part, so let me just briefly sketch how the argument goes. So it's a fact for modal logic that if you look at the finite total relations, total meaning any 2 points are related to another, all relations hold, that this is complete for S5. So all axioms of S5 hold for finite total relations. If something isn't in S5, then you can find some large enough total relation in which it's invalid. So a good example of this would be something like, if P is true, then P is necessary. This is just not in S5, and you can recognize this by looking at a frame with 2 objects. P is true here, not true here. So P is true, but it's not necessary because you can access this world where it's false. Okay. So how does that help us out? Because we're not looking at finite total relations. We're looking at this like trans-finite tower of these V kappas. The idea then is we want to get what we call control statements. These are going to allow us to somehow mimic the structure of total relations within Zermelian potentialism. So we kind of want to take a certain quotient that respects truth with regard to these control statements. And so we can port over the example giving invalidity on a finite total relation back into our Zermelian context. Okay. So what are we going to use? This is what we call a switch. So what is a switch? It's the statement you can freely toggle on and off. It's possibly true, possibly false, and that's true at any world. You can turn it on, make it true, turn it off, make it false, can do it freely. And then a bunch of switches, we'll call them independent if you can just toggle them freely without affecting the other. So I can make switch 1 true without affecting the values of all the other switches. Okay. And so the theorem here is that if a potentialist system does have arbitrarily large finite families of independent switches, then you get an upper bound of S5 for the modal validities. And why is this? You take maybe you have a frame with 4 elements. This is your total relation, 1, 2, 3, 4 elements. Well, if you have 2 independent switches, you can have false, false, true, false, false, true, true, true. Those identify basically the 4 points in this total frame. And you can then mimic whatever goes on there by the values on the switches. And so this allows you then to anything that wouldn't be valid on this finite total frame, you just mimic by playing around with these switches. So if your potentialist system has switches and they're independent, then you get an upper bound. More firmer upper bounds, you're going to use more complicated control statements. Okay, so how do we get switches for Zermelian potentialism? So the idea then is we look at our current world or current V kappa, and we're going to look downward because we want to express something without the modal language. These switches, these sigma, aren't supposed to refer to diamonds and boxes, just the set-theoretic language. So we have to look downward at what we have already built up, and we're going to ask, how many inaccessible cardinals have we built up so far? As we build up higher, we get more and more inaccessible cardinals. Let's look down. So the ordered type is either goes all the way through the ordinals, or else it's some bounded ordinal. If it's bounded, we can write it as the limit ordinal plus some finite ordinal. So let's write it as this limit plus finite, lambda plus n. And our switches, we're just going to look at n, and we're going to look at its binary expansion. So maybe we have a limit ordinal that's +0. And if that's what we're doing, +0, then all the switches are off. If we make it +5, then we have 1, 0, 1. So we have 2 switches off. So this gives us, by making it arbitrarily large, we get these independent switches. You can freely expand. If it was +5, you could go add omega and then add whatever you want to turn it to whatever you want. So we get these independent switches. We can freely toggle on and off, letting us kind of mimic this invalidity of anything outside S5. Okay. So S4.3 is lower bound, S5 is an upper bound. There's a bit of a gap between these modal theories. Can we fill in that gap to any extent? That's the question. Okay, so let's look at some more control statements to try to fill in that gap. So button is something that once you push it, stays pushed forever. So in other words, it's possibly necessary. So one way you could think about this axiom 5, possible necessary P implies P, any statement like possibly necessary P, that's a button. So 5 axioms says you already pushed all the buttons. That's a way to think about it. Okay, so here's a button for Zermelian potentialism. Fix an ordinal xi, and beta xi says that there's at least xi many inaccessible cardinals. Well, once you make this true, once you've built up enough to say see 7 inaccessible cardinals, as you keep building up higher, you're always going to have at least 7 inaccessible cardinals. You don't get rid of them. It's this inflationary growing upward domain. So once you push it, stays pushed. Of course, before you've built up to have 7 inaccessible cardinals, it's not true yet. But once you get high enough, it stays true forevermore. It's possibly necessary. Okay. Then we can use buttons to do a little bit more. So this is what George Liebman, who introduced the idea in the context of modal logical forcing, called a long ratchet. The idea is you imagine like you have this sequence of buttons, and pushing one button pushes all previous buttons on the sequence. So this is like giving you a yardstick where you can keep going upward, but you can't go back. So like the metaphor of the ratchet is you can twist it one way, but you can't twist it back. So you push these buttons and you can't go back. So these buttons I gave you at least xi many inaccessibles, that's going to form a ratchet. If you have at least 2 inaccessibles, you have at least 1. If you have at least omega many, you have at least 1, 2, 3, 4, and so on, everything less than omega. And so what Liebman showed using kind of a more complicated argument of what I sketched about S5 with these finite total orders is that if you admit a long ratchet, then as long as you haven't pushed all the buttons on the ratchet, you're going to have S4.3 as an upper bound for the modal validities. Basically, this allows you to mimic the class of complete frames for S4.3, finite linear preorders, by looking at positions on the ratchet. If it was already pushed, of course, you couldn't do that. Okay. So when have we not pushed all the buttons on this ratchet? Well, the only way we've pushed all the buttons is if at our V kappa, there's an unbounded sequence of inaccessibles below. Because from V kappa's perspective, there's an inaccessible for every ordinal. V kappa's ordinals are kappa, there's one for everyone below. So as long as kappa isn't a limit of inaccessibles, this gives us exactly S4.3. S4.3 is lower bound, got it as the upper bound. Okay. So for example, if you're the third, V kappa is the third world in the sequence, there's only 2 inaccessibles below, 2 is bounded in kappa, so it's going to have S4.3 as its modal validities. Okay. The problem with this is that you can have inaccessible cardinals, which are limits of inaccessible cardinals. So if you've studied large cardinals before, this is pretty ubiquitous. For example, a measurable cardinal, a model cardinal, weakly compact, all of those are inaccessible limits of inaccessibles. So this doesn't completely answer the question because there might be worlds that are strong enough that this ratchet is completely filled out. Okay. So in particular, say that kappa is too inaccessible if it's inaccessible and the inaccessibles are unbounded below kappa. It's an inaccessible limit of inaccessibles. So rephrasing what I said in the previous slide, if kappa is not too inaccessible, it validates exactly S4.3. Okay, what about if kappa is too inaccessible? Well, if it's not a limit of 2 inaccessibles, we just repeat the same thing. Instead of asking how many inaccessibles exist, we ask how many 2 inaccessibles exist. Maybe kappa is the smallest to an accessible cardinal, in which case nothing on the ratchet has been pushed. We got plenty of room to move upward. Okay, but what about a 2 inaccessible that's also a limit of 2 inaccessibles? Those are called 3 inaccessibles. What if kappa's like that? For example, any malo cardinal is 3 inaccessible. Well, as long as kappa isn't 4 inaccessible, we just ask how many 3 inaccessibles exist. Okay, but what if kappa's 4 inaccessible? Well, okay, then we can ask about that. What if it's 5 inaccessible? And we want to know, can we always pull this kind of trick? Or if we get like kind of strong enough large cardinal properties, are we catching our tail somehow? Okay. So the answer, it turns out, is no, we can't always pull this kind of trick. So let me talk about why we can't always pull this kind of trick. So let's say kappa is sigma 3 reflecting, if it's inaccessible, and it's a sigma 3 elementary submodel of the whole universe. So this is stronger than all these n inaccessibles, and it's weaker than, for example, a malo cardinal in strength. If order's malo, we can get these guys. Okay, so not too strong in the large cardinal hierarchy. And then the result is that for the sigma 3 reflecting worlds, these ones will validate exactly S5. So S5 before was the upper bound for all worlds. These worlds exactly reach the upper bound. Okay, and really briefly, the idea is saying that there's a world that thinks phi is possibly necessary. That's a sigma 3 assertion. So sigma 3 reflection is precisely the amount needed to reflect things like that below and back up, which is what allows you to get that V kappa thought it was possibly necessary. It's already true in V kappa. Okay, I'm going to skip that in details and just say that. Okay, so kind of summarizing the situation then for Zermelian potentialism is under suitable large cardinal assumptions, which are kind of swept under the rug, the modal validities at any world are bounded below by S4.3, above by S5. And some worlds are going to get exactly the lowest bound. Some worlds are going to get exactly the largest bound. Okay. So you can maybe ask more. You could try to like more firmly delineate the boundary between the two. Is it possible of anything strictly in the middle? But I think this answers really all the big questions. So Hampton's Linnebo kind of mostly answers this. Okay. So was that a question? Okay. So I want to kind of switch gears and talk more generally. So the general setup, this definition is due to Shapiro and Linnebo, is a potentialist system that we specialize to set theory, is we take a bunch of models of set theory ordered by a reflexive transitive relation which refines the substructure relation. So the way I like to think about this is you can do model theory for like a universist view of sets. There's one universe of sets. What are the model theoretic properties you can try to use to express that? These potentialist systems give us a model theory for ideas about sets that are more multiverses. Rather than having one, you have many, and how do they relate? What can you say? You don't just want to know what an individual world looks like. You want to know how it fits in this larger structure. So the Zermelian potentialism we looked at, this was exclusively about height. When we added more sets, they got higher and higher up in rank. We had to iterate the power set operation more and more. If you've seen much set theory, then you know that set theorists like adding sets of low rank. So forcing, for example, co-enforcing, we add lots of new reals. Those are very low in rank. So we're adding new sets. We're kind of making the universe wider rather than taller. So can we have a potentialism where we can get wider and not just taller? Will this have different properties? Okay. So one way you might do this is what Hampkins and Linnebo called a countable transitive model potentialism. So transitive model is it just really has the true membership relation restricted to some countable set. Okay. So if we look at just these countable transitive well-founded models, that's going to give us a potentialist system. We can do width extensions because the forcing lemma applies to countable things. We can externally build a generic, make it wider. We can make them taller under suitable consistency assumptions and so on. Okay, why countable? Because if you don't restrict to countable, eventually you just have all of the sets up to a certain rank, and this is not a good model for this sort of view. So we want to do it so that externally you can always make it wider. Okay, and I'm going to skip the details, but I want to mention that in the same paper, Hampkins and Linnebo also computed the modal validities for this sort of potentialism. So the lower bound now is weaker than S4.3, it's S4.2. It's a little bit weaker, and S5 is still the same upper bound. and similar sort of thing, each bound is achieved at certain worlds. So we're seeing different sort of structured modal truths for this height and width potentialism versus just this height potentialism. Okay. They use a different set of control statements to get this, of course. That's how you get the upper bounds. Okay. So I want to then just briefly talk about a very different flavor of examples from these two. Okay. So let me make some general definitions about models of set theory. So end extension is you add new elements, but you don't add new elements to old sets. So if you had an old set, you can't add a new element to it when you extend. So this would be like a forcing extension, for example, is an end extension. You add new elements, but only to new sets. You can't add anything that already existed. All these elements also already existed. And you can also say, moreover, a rank extension is you have your model, is you only add new things on top. You had to iterate this power set operation, this V alpha hierarchy, higher up to get it. So like Zermelian potentialism with these V kappas getting higher, those are all rank extensions. So what's new about these definitions from what we've seen then is I'm not requiring any of our models to be well-founded. So these definitions just make sense for arbitrary models of the axiom of set theory. You just can say this, you can say this is all fine. Makes sense for ill-founded models. We can ask about that. Okay. And so these two notions of extension give rise to different notions of potentialism. So let's call them end extensional and rank extensional potentialism. End extensional is you just order things by end extension. You can add new elements, but you can't kind of add them to things you're already committed to. Rank extensionalism is you can add new elements, but they have to have higher rank. They have to come above. And so this is kind of giving an ill-founded analog of these two previous things we saw. Countable transitive model potentialism, everything was well-founded. Zermelian potentialism, everything was well-founded. We wanted the same sort of extensions, but not require everything adhere to some external standard of well-foundedness. Okay. And probably not too surprising, once you let ill-founded things into the picture, things get very weird, things get very different. Okay. So both of these are going to have exactly for all their worlds, S4 as their modal validities. So S4, since you like me probably forgot the list of axioms many slides ago, that just expresses that the accessibility relation is reflexive and transitive. So that's just trivially going to be a lower bound for any potentialist system because we've just required that our relation be reflexive and transitive. And so this is saying as few things as possible are valid. Okay. Not so surprising, you let ill-founded models in. Now you can kind of do as much as possible. Okay. I'm going to skip this step or talk about it. They just follow a similar strategy. You basically have a uniform definition for a finite sequence that you can freely extend by moving up your potentialist system. Okay. And that gives you control statements to get S4 as an upper bound. Okay. So why care about any of this? I think that's a great question. And part of the motivation for this is that this gives you a better refinement of what sort of philosophical commitments you might have. So if you're familiar much with philosophy of set theory, you'll know that there's kind of this active universalism versus multiversalism debate. Should we have one universe, many, how do they relate? And this gives you a kind of a refinement of what a multiversist view might have. So let me say a little bit more about this S4 thing. So these two potentialist systems from the last slide, the ill-founded ones, these kind of are radically branching forms of potentialism. As you extend, you're making decisions with permanent consequence. So any failure of point 2 is there something that looks like it could be possibly necessary, but you can just extend to make it so it's actually impossible. So for the rank and n-extensional systems, this is as you extend, you have this uniform definition of this universal finite sequence. You're committing to what's on the sequence. I put 3 on. Once I put 3 on next, I can't put anything else in that entry. Okay. And so very briefly then, the idea then is this shows that suppose you have a Zermelo style view, you think we have this dynamically growing multiverse of larger and larger universes getting higher and higher. Well, the modal structure of truths in your multiverse is going to depend upon how you feel about well-foundedness. Is there an absolute notion of well-foundedness that applies to everything? If so, you got S4.3. If you think that there's no absolute, no definite notion of well-foundedness beyond just what an individual model thinks, you're going to have much weaker modal validities. So it gives you this refinement of what's going on, kind of highlights that this notion of well-foundedness is playing an important role. Okay. So could say more about set-theoretic potentialism. I want to move to the second half of my title. Okay. So motivating this talk then is some collections, such as the collection of all sets, the collection of all ordinals. These are too large to be sets. If you try to make them sets, you get into the Russell paradox, the Biroli-Forti paradox, stuff like that. Well, if they're not sets, what are they? So one possible answer we just talked about, Zermelo's classes are just sets in a larger world. So you thought you had all the ordinals. Nope, larger world actually sees that's just a set. Okay. Zermelo's answer isn't the only one. Maybe you're really convinced by it, but lots of people have tried to give answers to this question. So I want to focus on a species of answers which takes the sets as fixed for now. Okay. So let me just briefly explain why I think this is something that actually needs work to be done. So a popular answer, you'll see this in like Yek's set theory textbook uses this approach, Kanemaru does, kind of all of them do, is talk for classes is just convenient shorthand for definable properties. So when we say xi is an ord, we're not saying there's a set xi, there's an object ord, that's the collection of all ordinals, and this object is an element of this other object. It's just a shorter way of saying that xi is transitive and linearly ordered by membership. So it's just a convenient shorthand. And we know that a lot of things that look like they need talk about classes, inner models, elementary embedding, stuff like that, can be interpreted as just quantifying over sets. So why isn't this good enough then? Why do we need more than this? Why is there an actual problem? Okay, so problem is some classes that we want to talk about just aren't first order definable. So if we only have first order definable classes, it's insufficient. So let me just briefly look at two examples. So Kunin's inconsistency theorem says there's no non-trivial embedding of the universe to itself. Basically, this is an anti-large cardinal theorem, says that if you try to have these embedding-based large cardinals, measurable cardinals, extendable cardinals, supercompact cardinals, etc., they top out after a certain point, you just get inconsistency. Okay. If the only classes are the definable classes, this is trivial. Every non-trivial elementary embedding has to move an ordinal. So there's the smallest ordinal it moves, its critical point. That's definable. So if your J was definable without parameters, it would have to move its critical point, but it would have to fix its critical point, contradiction. And then a small extra argument yields that J can't even be definable with parameters. So completely trivial if you only have definable classes. So if you think, as set theorists as a whole do, that Kunin's theorem has substantive content, it has to be because we want to look at non-definable classes. Okay. And the second example I want to mention is class forcing. So I'm not going to define any of these things. They're highly technical. There's a certain technical notion, pre-tameness. If your class-sized poset is pre-tame, the forcing relations are definable. If it's not pre-tame, they're not. And indeed, you can exactly characterize what you need. So if you want to talk about class forcing in general, we need undefinable classes because we want to have the forcing theorem. We want to say you can, get truth in the extension by looking at this forcing relation of the ground model. And so we need certain kinds of undefinable classes, truth predicates in this case. Okay. So we want to be able to talk about classes. We want some to be undefinable. And so there's been various proposals to how to think about this. So some of them fit naturally into the sort of potentialist framework that I talked about with Zermelo. So potentialism about classes, not potentialism about sets, same sort of framework though. So the project with Neil is, okay, so potentialism for sets, the hope was that this would better help us understand kind of what's going on with the debate about set theory. And perhaps the same can be done to kind of refine our understanding of different proposals for what classes are. Okay, so let me just look at a couple of answers, just because that kind of motivates this. So one is best done by Kentaro Fujimoto in some recent work. So he wants to do what he calls liberal predicativism. So usually when people think of predicativism, if you think of like Pfefferman or Weil, you're starting with the natural numbers and you're building up from there to sets of natural numbers. Fujimoto wants to start with the universe of sets as a fixed object and look at classes over that. And, so he's saying, how do we interpret the class quantifier? There exists a class X. There's a predicate we may admissibly introduce. And so they're distinct from sets because they're predicates. And Fujimoto explicitly wants to look at more than just definable classes. And for example, he wants truth predicates. Okay. Another one with kind of a similar feeling comes from Oisi and Linnebo. And so he proposed a theory of properties in which properties are kind of built up in a hierarchy. So there's Russellian issues with just trying to let all properties take the property of not being applied to itself. Then you can sort of get the Russell paradox and properties with that. So Linnebo wants to have a hierarchy of properties to avoid these sort of vicious circles. And he wants to build them up along the ordinals. So there's the starting point where you just look at your properties or just things you can talk about first orderly, and you build up from there. Okay. They're not actually classes, but you can interpret class theory by just looking at extensions of properties. So it ends up being very similar. And then he has this hierarchy of classes. You kind of add more and more as you individuate more and more properties. Okay. So what's common about these approaches? Why did I talk about them together? So one is they're both starting with the sets as a fixed totality. And two is you can kind of see both of them as they're building up classes by allowing more and more. You start with some basic starting point, and you add more and more classes building upward. So it's very similar to this Zermelo picture, where you kind of start and you build upward more and more. Now the upward is adding more classes, not more sets, but this gives you a natural interpretation in a modal framework. Less clear from what I quoted, but this is an important point, is for both of these views, both Fujimoto's and Linnebo's, iterated truth predicates play an important role in measuring how many classes exist. So very briefly, what is an iterated truth predicate? So Tarski, way back when, proposed this sort of hierarchy to languages. You have your object language. In our case, that's just being able to talk about sets. You can have a truth predicate for the object language, truth about the universe V. But now we can take this truth predicate and we can ask what is true in the language that can refer to the truth predicate. So we get truth about truth, and then we can iterate this truth about truth, and so on transfinitely. And so an iterated truth predicate is just a device to make this hierarchy a single object rather than a meta-theoretical many objects. And so an iterated truth predicate has a length. That's just how many steps of truth about truth did you do? Possibly could be transfinite. Length could even be larger than the ordinals. Maybe you could have like a whole ord length thing, and then have another ord length thing on top of that. Okay. And you can get a formal definition, but it's long, technical, and not at all illuminative. So I'm going to skip that. Okay. So because these iterated truth predicates play an important role in both Fujimoto's and Linnebo's systems, it kind of suggests a possible potentialist way of looking at this. So let me fix a world to be the sets. Both of these have fixed sets, so we're not looking at multiversum for sets, just a multiversum for classes. So let's say that a truth predicate system is certain worlds with classes over our sets M. Okay. So one thing is we want our worlds to kind of be nice. So they should satisfy predicative comprehension, class replacement. Predicative comprehension, just as if you can define something in a first order way, it exists. So that's like a closure property. Class replacement says you can't define a short cofinal sequence in the ordinals. So usual views of set theory is that's bad, so we just want to exclude it. That's just basically to avoid noticing our models countable, basically. Okay. And we have to have a starting point for both these positions. So the starting point is the definable classes are kind of there. We think that anything you can talk about in a first order way, that's a class. We just want more than that to build on top. So how do we build on top? Since truth predicates play the important role, the basic way you can do it is to say, if you have a world and you have a class, there's a larger world that has the truth predicate with that class as a parameter. You can kind of make a modification. So rather than just vanilla truth predicates, you can have iterated truth predicates of any length. This is giving you a modal version of Fujimoto's approach because he wants to have unbounded length truth predicates for what he's doing. And alternatively, you could modify it So maybe you want to allow iterated truths, but they're bounded in length. So you can add a new truth predicate, but it's got to have length an ordinal, like a set sized length. So that corresponds to Linnebo's approach, where you're individuating along the ordinals. So you can go up maybe omega 1 far, omega 2 far, whatever, but you'd never go beyond the actual whole class of ordinals in length. Okay. So some basic facts, let me go through this. So this puts restrictions on the sets. You have to have iterated consistency statements, etc. And if your world is well-founded, your sets are well-founded, you have a unique truth predicate. The externally defined one matches it's unique. And there's going to be a smallest truth potentialist system in a certain sense. And what are the worlds? It's just, you look at what's definable from the length, finite length iterated truth predicates. You just build up from there. So you have definable classes, definable from truth about truth, and so on. If you have bounded length, you get the same fact. You just need to allow longer lengths. So if you want to have, for example, length less than OR, you just look at iterated truth predicates of length less than OR and what's definable from those. If you have unbounded length, you get it with a certain extra technical condition I'm going to skip over. Okay. So kind of the first result about we have this then is that for the smallest truth potential systems, the sort of natural models for Fujimoto or Linnebo style potentialism is S4.3 is a lower bound. And if your lengths satisfy this closure condition, can close under addition or less than omega squared, you get exactly S4.3. So we get an exact calculation for the lower bound. This is linearly ordered. So S4.3 is free, like we talked about before. For the upper bound, we needed a control statement, a long ratchet. And okay, for Zermelo, the long ratchet was there are so many inaccessible cardinals. Now we say there are so many iterated truth predicates. That's going to give you a long ratchet. It's a similar sort of idea. We build up in a hierarchy. This is giving you what you need. And the point is you can refine Liebman's lemma about getting S4.3 from long ratchets to just need this fact. Okay. So that's fine, but things are more complicated. And specifically, so the motivation for going beyond definable classes was to get all the uses of classes, basically. And some classes we want to use are global well orders. Global choice functions, global order is equivalent in this context, really. So this is used in determinacy for arguments, for example. This is used, for example, to prove facts about the surreal numbers. Global well orders might not be definable. They can be, for example, if you have a model of V equals L, then you have the L order, that's a global well order, that's definable. But in general, even strong axioms for classes don't guarantee you get a global well order. But easy to add it by forcing, and you don't have to add sets. So what do? It's the natural thing if you've done forcing, you take set-sized partial well orders. The generic extension there is going to be a well order of the entire universe, a global well order. And neat fact, this is forcing equivalent to adding a Cohen generic class of ordinals. So I'm just going to think about this as our forcing is we're adding a Cohen generic class of ordinals. Okay, so it's just adding class of ordinals that's random in a certain technical sense. Okay, so if you're a class potentialist, you want global well orders so that we can do all the things to do with classes. So one alternative is you say, okay, global well orders have to be first order definable. This has substantial cost. You're requiring the sets to satisfy a certain axiom. Okay, so maybe you don't want to pay that cost. Maybe you want to do something else. So maybe rather than starting with the definable classes, you want to start with definable relative to a truth predicate. Some modification. So Neil and I showed then that this changes what the modal logic is. If you start with a generic global well order in the base world, instead of getting S4.3 exactly, you get S4.2 exactly. So you get a weaker modal logic. I'll skip the proof. Another alternative is maybe you don't like that. Maybe you just want to change the extension rules. Start with definable classes. You can extend to get more truth predicates, or you can extend to get a global well order. Different way you might try to implement this idea. Global well orders might not be definable, but you can always move to a larger world where they exist. This can be even more destructive. So the problem is this lemma, what it says, there's Cohen generics that kill off the possibility of ever having a truth predicate. So you can find a carefully built Cohen generic C so that you can't have it and the truth predicate in the same world. you will basically be able to see that your model's countable. And there's a relativized version of this. So this gives a rather nasty failure of the point 2 axiom. If you want to say truth predicate exists, that's possibly necessary. Truth predicates are absolute. Once they exist, they stay truth predicates forever. If we added this Cohen generic, we can never add the truth predicate. This possibly necessary thing saying truth predicates exist was made impossible. Okay. Okay. And indeed, this lemma has consequences for other things. I'm going to skip. Okay. So summary really quickly, what this kind of shows is that once you introduce global choice, there's now sort of a dichotomy made. You have to pay a cost somehow, and maybe you can argue for one way to do it or another, but this kind of shows something's going on, something you have to justify. Okay. So let me just skip the conjecture and future work slide, and thank you for listening.